far I have discussed with you different types of binary phase diagrams in which liquid phase is present, and then I am in the subsequent lectures I am going to discuss about solid state phase diagrams, binary phase diagrams, but in between I want to let you know that the genesis of this kind of different phase diagrams. So, there are a lot of studying from ab initio calculations to thermodynamic calculations, why different kind of phase diagrams evolve or forms, and like why you have isomorphous systems, eutectic systems, peritectic phase diagrams and monotectic phase diagrams or syntactic type phase diagrams. Why this different type of phase diagram at all form in the real systems, and this can be answered from different angles. The easiest one is the thermodynamics approach. You can use the thermodynamical concepts and come up with this with explanation for that, and you can also use kinetic approach and to explain that, but that not I am not going to do that. And finally, one can also use ab initio approach, that is you can take two atoms and using their pair potentials you can calculate the phase diagram. That is very generic and very complex also, because you need to know the pair potentials. Not only that, you also need to have a good computational facility to do that, but for your understanding for a course like this we need to consider the thermodynamical approach, and that is what is known as quasi-chemical approach in the actual thermodynamical sense. So, we will consider atoms when we talk about this approach. Let me first explain what will happen. Let us suppose we have a system with two atoms A and B. There are two atoms A and B, correct. So, this talks about the interaction between A and B. I know that if I have two atoms A and B, there are three types of bond possible. One is AA type, other one is BB type, and third one is a AB type. There are only three types of bond possible. You can have bond between A and A, bond between B and B, and bond between A and B. There are three different types of bond possible. Now, if you have a system in which all kinds of two atoms are present, and these three different types of bonds can form, and total energy of the system can be given number of bonds of AA type, suppose this is XAA, and multiplied by bond strength of AA bonds, right. This is the energy, total energy of the AA bonds in the system. If you know the number of bonds of AA type and if you know the strength of the AA bond, then these two multiplication will give you the total energy of the AA bonds. Similarly, for BB bonds, if this is the number of BB bonds YBB, and this is the strength of BB bonds, this is what is the energy of the total BB bonds, and finally this is the number of AB bonds W small w AB into energy of AB. Total summation will give you the energy of the system. That is clear. Atomistic that is what is happening. Okay, now this is nothing but enthalpy of the system. Why? Because enthalpy of the system is connected to the bond energies. If I have two atoms, then this is what will give me the enthalpy. So, sometime we write total enthalpy of the system is XAA multiplied by enthalpy between two AA bonds plus BB, number of BB bonds, multiplied by enthalpy of BB plus total number of bonds of AB multiplied by bond and enthalpy of AB, correct. So, from here to there, when I transpose from here to there, difference is that I have replaced the bond energies by enthalpy. It is almost similar, that is not much difference between HAA and EAA in quasi-chemical theory. So, now question is that this is enthalpy. So, as you know, the free energy of the system is given by enthalpy minus Ts. So, I need to also calculate entropy, but in the first class, in today's class lecture, I am going to tell you how we can get enthalpy. Okay, enthalpy is a very important parameter, and that is what actually most of this phase diagram variations depends on. So, enthalpy can be calculated using this approach, and how I am going to do that, that is what I am going to show you today's class. In the next class I will discuss how we can get entropy. In fact, that is what I have already done in the very beginning of this of the semester. So, I am now not only going to borrow that formula for entropy and discuss further, I am not going to derive it again, but for enthalpy I need to derive the full relationship so that you understand. But what I suggest you is that when I am doing this formulation, you must follow step by step, take a paper and pen and follow my steps, then only you can calculate and get a proper understanding of this concept. So, quasi-chemical approach assumes that the bond energies are equivalent related to the enthalpy of the different bonds. So, now let us suppose the system consisting of total number of atoms n, and this is total number of atoms in the system, and also assume that z, small z, is the coordination number of the system. I will explain what is it. What is the meaning of coordination number? Well, somebody says in BCC coordination number is 8. What is the meaning of that? Okay, very simple. You draw a BCC unit cell, this will be clear to you. There are atoms at the corners, 8 corners, and there is an atom at the center. So, very simple, the coordination number of this atom is 8 because it is bonded with all the 8 atoms. This is the first nearest bonds which they form, correct. That is why this is Z value is 8. For FCC, Z value will be 12, that is very clear. So, that is what is Z. So, when you form a solid solutions, then you are basically changing these different bonds. Suppose you form a solid solution between A and B, A might sit here and B might sit at the corners. So, therefore, AB there will be 8 AB bonds, a coordination number of A will be 8. So, if I have total number of bonds atoms in a system is n and Z is the coordination number, what is the total number of bond possible? Very simple, total number of bonds is how many? That will be multiplied by n into Z, divide by 2. Why 2? Because you know for every atom there is only one only one bond is possible. Suppose there is A atom and B atom, there is only one bond, okay, but you are counting 2 atoms. So, therefore, if total number of atoms are n, total number of coordination number is Z, n day by 2, half of that will give you the total number of bonds present. Is it clear? Very simple. I have A atoms, it has 8 bonds together with 8 atoms, okay, but you know number of atoms are 9. So, if I take a large number of atoms, this will be coming like this, n Z by 2. So, if this is the total number of bonds present, now how I can calculate number of AA bonds, number of BB bonds, number of AB bonds, how we can calculate? Well, that can be calculated using very simple formula, very simple concept. What is that concept? Okay, I know that in a solid solution the A and B, amount of A and B presents, and you have probably seen in all the phase diagrams I am presenting the concentration in terms of mole fraction XB XA, because I told you at the beginning of this semester that the mole fraction is the widely used compositional variable used in the phase diagrams. So, suppose I have in alloy mole fraction of A is XA, this is the mole fraction of A in the alloy, mole fraction of A. What does it mean? That means the probability of finding an atom A in the solution is XA, because XA is a fraction and any probability will be a fraction. So, if XA is a fraction and XA denotes the mole fraction of A, so that means XA is also equal to probability of finding A, in a site, correct. That is obvious because that is the fraction and that is the mole fraction of A. Similarly, xp which is equal to x1 minus xa is the mole fraction of B and is equal to probability of finding B in a site, correct. So, now if I have atom A here and I want to find another atom A here, so that A bond forms, this is A, this is A. So, probability of finding this atom is xa. Now, probability of finding this atom is also xa nearby. So, the probability of A bond, probability of AA bond is what? Probability of AA type bond formation is xa multiplied by xa square. Why it is so? Well, as I told you, xa is the mole fraction of A, which is nothing but probability of finding A in a site. So, if I put a lattice point here in a solution, suppose atomic structure, the probability of finding this atom A is xa. Now, probability of finding another atom in the next site, a neighboring site A atom is also xa. So, probability of forming this bond AA type bond is xa multiplied by xa, that is equal to xa square, correct. Similarly, probability of finding a BB bond is what? 1 minus xa into 1 minus xa, that is equal to 1 minus xa whole square, correct. So, now I have got these numbers, okay, probability of finding xa, probability of finding xb bonds, AA and AB bonds. What is the probability of finding AB bonds? Probability of finding A is xa, probability of finding B is 1 minus xa. So, probability of finding AB type of bond is xa multiplied by 1 minus xa. Now, you know AB can be looked at AB or BA, bond is same, whether it is between A and B or B and A does not matter, it is AB type of bond. So, for this also it will be xa multiplied by 1 minus xa. So, therefore, probability of finding in AB bond is this plus this, that is equal to twice xa minus 1 minus xa. Is it clear? If it is not clear, try to understand. Probability of finding in AB bond is same as probability of finding a BA bond, because the bond is between A and B or B and A does not matter, it is a AB type of bond. So, now for this case, if I have this type of A sitting first, B sitting next, what will happen? Probability of finding A is xa, probability of finding B is 1 minus xa. So, probability of finding A and B in the nearby region or neighboring points is xa multiplied by 1 by xa. Similarly, for B and A, like that configuration, probability of finding B is 1 minus xa, probability of finding A in the neighboring position is xa. So, probability of finding B and A in the neighborhood region is xa multiplied 1 minus xa multiplied by xa, okay, 1 minus xa multiplied by xa. So, the probability of finding AB bond is equal to this plus this, because both the situations are likely. So, that is why we have to add, and if you add we get 2 into xa minus xa into 1 minus xa, correct. So, that is obviously the way it has to be done. Now, I rub up these things and go back to the number of bonds formations. You have noted down, otherwise, okay. So, now question is this, I have total number of bonds is nz by 2 as I told you. So, xa is nothing but nz by 2 multiplied by xa square, because that is the AA bonds xa square. So, this is what is your xa, and HA is remaining same, HAA plus number of BB bonds is again can be calculated nz by 2 multiplied by 1 minus xa whole square into HPB plus this is what we should write twice xa, sorry, nz by 2, nz by 2 is going to come twice xa 1 minus xa, this is the whole thing for WAB multiplied by HAB. So, look at these derivations. So, we have found our number of bonds of AA type multiplied by HA, that is given by NZ by 2 into XA square. NZ by 2 is the total number of bonds of A in the system, multiplied by XA square will give you probably total number of A bonds. Similarly, NZ by 2 divided by multiplied by 1 minus XA square whole square will give you total number of BB bonds, multiplied by HAB will give you the total number of total bond energies of BB bonds. Similarly, for AB bonds you can do that. So, now once you have got this is a very important derivation. Once you have got this, you can do lot of things. Let us rewrite this sentence a little bit nicely, rewrite the derivation. We can write these things in a simple manner. Okay, I do it here. HA is equal to NZ by 2, I will take common, NZ by 2 I will take common. So, then it has become XA square HAA plus 1 minus XA square HABB plus 2 XA 1 minus XA into HAB, right, that is what you will get. So, now I can actually write down this sentence nicely. How we can write down? NZ by 2, this can be written in a little bit different way. What is that? I need to take common XA, yes, let us do that, and if I do that, then what will happen? Yes, XA multiplied by HA plus 1 minus XA whole square by XA, because I have taken common, into HPB plus 2 1 minus XA into HAB, right. I can write this way, and this can again be further modified, rather this can be further modified like this: XA HAA plus XB HBB plus XA 1 minus XA common, this is like this, HAB minus, yes, minus HAA plus HBB by 2. This can be written like this. So, I can remove this step, this is not required. From there I can get down. How I get down? Basically this is simple. I add some quantity here, some quantity there, which I subtract. So, you can clearly see this is nothing but NZ, okay, enthalpy of the pure system, XA HAA, XA XB BHB plus the enthalpy difference because of addition of because of mixing. So, what I can do is that this part, oops, yeah, this one is nothing but enthalpy of A, pure A and B in a mixture. On the other hand, this is for the mixing, So, rather what I can do, I can write down H, this is H is equal to H1 plus delta H, and where H1 is this NZ by 2 XA HA A plus XP HBB, XB is nothing but 1 minus XA, and delta H is given by twice, or sorry, not twice, NZ XA 1 minus XA, you can keep it XB also, multiplied by HAB minus HAA plus HBB by 2, right. So, that is my H delta H mix, that is the enthalpy which forms because of mixing A and B atoms, that is the enthalpy. As you can clearly see, N is a positive number, Z is a positive number, N is number of atoms which will be Avogadro number, Z is the coordination number which is a positive number, X is a positive number, 1 minus X is a positive number. So, the positive of negativeness whether of delta H mix depends on this number in the bracket. So, there what is this number? This is nothing but enthalpy of HAA minus enthalpy of HAA plus HBB divided by 2. So, if the difference of the uneven bonds or difference between the bonds of AB minus average of A and BB, that is it. So, the sign of this will completely depend on this parameter, sign of this will completely depend on this parameter. So, we can explain from this very nicely. What is that? We can say that if in a system AB bonds are easy to form, then this will be positive, because then HAA, so no, then this will be negative, because this will have lower energy than this one. So, because this will have lower energy, because the probability of formation is higher, then this will be negative. So, in that case, if delta H is negative, free energy system will also be negative, because entropy is always negative, T minus Ts is always negative, because entropy is always positive. So, that is why. So, but on the other hand, if suppose the bond formation is more likely, like for the similar pair A or BB is more favorable than AB, then what will happen? This will be positive, and if this is positive, then it can create different kinds of situations in the free energy curve. So, I am just going to leave this derivation or this particular equation to you to understand in detailed manner and derive the way I have done it, and once you have done, in the next class I will take from this and add, also derive entropy, and this is I have done for enthalpy, I will do for entropy, and finally I will derive H minus Ts and show you how different kinds of free energy curves will appear, and that will dictate to different phase diagrams. So, I just leave it with you these particular things, so that you analyze there in the book very nicely. Any phase diagram books, I told you both the books has this particular derivation nicely done, even you can find on internet also the total derivations. Okay. So, we will see in the next class.